Let's roll. Oh, we're already rolling. Okay. All right, so I got some feedback back from the people that watched this on YouTube. They say it's frequently difficult to hear questions and that you all should be swallowing the microphone whenever you ask questions. And they say it's good that I'm generally repeating the questions, but they would like to hear your melodious voices as you ask questions. So please be careful to especially talk into the microphone whenever you're asking questions. Second bit of feedback was for the gentleman in the back there. How's it going? The feedback has been that there's a significant time delay between the time I start doing something on the board and the time you guys pan to the board. So the world of YouTube out there would love to see you guys being like really quick as I move around. Okay, I'm getting some nods back there. That's really cool. Okay, any questions that don't have to do with today's class? All right. Well, hopefully Will show up with a really smelly sandwich, and then everybody will be happy. We can all smell that all day. Okay, so the organization of this lecture is a little bit weird. Basically, it's not this super long lecture. It's actually not a very long lecture, but I have two other pieces where we can spend some more time that are in more detail in things. The problem was that lecture was in Keynote, and this one's in PowerPoint, and the export didn't work correctly, and I've got to tell my friends in the office team that PowerPoint breaks on that, and that's no good at all. So basically, I'm going to have to switch back and forth when I get there. But we'll see. I might not even get there at all. It depends on how much time we spend on the other things. What I do want to start with is just sort of my final slide from last time that we didn't really get to deal with. So we talked last week about GPU computing. And Dave Lubke and I made, he's the founding member of NVIDIA Research. We made this list actually 3 years ago. And we've updated it a little bit, but it's still a pretty good list of big picture problems in GPU computing. And so I want to sort of go through them. And if people have questions, you can ask. But these are things that we think are large and ongoing problems going forward. Okay, first problem is the killer app. And we talked about how GPUs are sold for graphics, and 99.99% of the revenue that the vendors get from selling GPUs is so that they can do graphics. And so one question for the GPU folks is, hey, what is the application that is going to have millions and millions of dollars of sales? Why are people going to buy $100 million of GPUs to do compute? Okay? What do you guys think? What are potential things where you'd say, people would buy $100 million of GPUs to do that?
Like virtual reality kind of applications.
Okay, virtual reality. So are you thinking people are going to have headsets in their home? Like you buy a Wii and it's got this cool headset that comes along with it, and you can do that with, user interfaces? Like, what are you thinking?
I guess I was just thinking more like most people who don't, like, I guess when people game, usually they're doing it to kind of escape their life. So kind of a Star Trek kind of.
The holodeck. The holodeck would be a wonderful application. I am all in favor of that. Okay, but entertainment applications. But then what do you need GPU compute for? Is that a graphics problem, or is that you're thinking the sort of compute behind that? I guess you're thinking the compute behind that. Okay?
I think one of the areas where they need more clarity is probably I think this could be a very small audience. But in the medical field, I think they need more accuracy, and they don't mind it being slow, but they want accurate data.
Okay, so in general, I mean, medicine is a place where we're going to be spending a lot of money as a culture. So not just in terms of diagnostics, which is sort of what you're mentioning, but in terms of prevention and monitoring kinds of things are really interesting. And so when we talk about sort of where do your flops go, we have all these flops, where are we going to spend them? Right now we can kind of model like an organ. We can model like your heart. And we can do a pretty good job of, showing how that works and fluid flow and so on and muscles and so on. We're nowhere near being able to model like an entire body and be able to say, okay, we're going to design a designer drug to be able to do this particular effect on your body with your chemistry and so on. So certainly medicine.
Search, like data mining, because there's so much data in the world right now. It's very hard to find a good and fast search that can search all of the data.
Okay. Search is enormous. And so both of these, actually all these things sort of come under, Intel has this vision that they call RMS, this recognition mining synthesis. So they see future applications, the future flops they're going to spin as being in this. And so recognition is sort of looking at the world or your problem and picking out the important things from it. So computer vision would be a recognition kinds of thing. Okay? You're doing the stock market and you're looking for anomalous transactions. You're looking at your body. Can you recognize things that are bad? Like, oh, you've got a chemical imbalance over here. Okay. Mining. Okay, and this is what Stanley's saying. Mining is how do you get information from a larger set of stuff. Okay, so this is stuff Google does all the time. It's what databases do. And then synthesis. Once you have the information that you recognized and you can go fetch things from mining, can you create a new scenario? Okay, well, medically, can you, if we did do this drug, what would actually happen? Computer graphics is synthesis. Okay, well, now we've created a scene. What's it actually going to look like? Okay, these are all problems that could potentially be good GPU problems. Okay.
We talked about earlier CFD simulations for oil, but also like weather simulations, since that's very important.
Okay. So if you model the world's weather today, you can do it roughly. You get down to the point where a cell in the global weather simulation is like 10 miles square. Okay? That's a lot of weather in 10 miles square, and the weather can really vary in 10 miles square. We're not even close enough to be able to do hurricanes on a global scale. Okay, so weather's a really hard problem. You've got this, butterfly flapping here affects the weather in China kind of thing. So, there's a long, long way to go, but certainly we can be more detailed than we are now. Okay, and which ones of these are going to sell something in the next 5 or 10 years? These are all great ideas for where we're going to spend our flops in the long run. What's going to be a business opportunity? And for me, that's sort of an unanswered question. I don't think anybody knows the answer. I'd love to look in 10 years and teach this class and say, yeah, it turned out it was this thing, but I'm not sure what that thing is going to be. Okay, problem number 2 is this issue of programming models and tools. And so we talked about stream programming model. Okay, we talked about SMPTE as kind of a way to think about doing computation. How do you think about the parallel programming model? Does it even look like a parallel programming model? Okay, what does the programming model look like? That's by no means established. And then tools to be able to work within those programming models. Okay, how can you have compilers that are going to help you do auto-parallelization or help you optimize your code? Very important problems.
Yeah, I had one question. Like a lot of these things that are done on, like in the TV world, like when they show some simulations of games or like ESPN shows some, those things exist in the TV world, right? It's not yet in a PC kind of a thing where a graphics chip does these things.
Well, so you mean like special effects kind of thing, or?
Right. Like if you want to do a simulation, like ESPN, I'm not sure if you've seen some.
I watch a lot of ESPN, so.
Yeah, the what-if scenarios that Tom Jackson shows. Like he has real players there. They run these simulations. Oh,
okay. So this is like, it looks like video game kind of thing. Okay. Actually, if you go buy Madden 2009 or something, actually the graphics are pretty decent. I hear. Not that I have this. I have a Dreamcast. It's pretty old. It doesn't look good.
Because, like in Grass Valley, right, there are these companies that do things for video.
Yes.
But it's not at come to your laptop or a computer.
So they're much better than they used to be. I can remember it was maybe 2001 and I was consulting in a company. It was the first time I walked into a room and saw a TV on and I said, where is it snowing right now that they're playing football? It was actually a Dreamcast in a football game. And it was like, that was the first time I saw it and I thought it was real on the first try. We're still a long way away. I think the visuals are pretty good. The physics are pretty bad. Yeah. But I don't think they're doing anything special there. They're not doing anything that, honestly, Madden 2009 isn't doing. But,
So there's nothing specific in the TV world that's...
Right. I don't think they have any magic. Post-production and TV kind of stuff is, the broadcaster kind of conventions are really important, and that's a place where GPU people hang out. Okay. What I want to concentrate on is not so much the graphics part, which is ubiquitous as far as GPUs go, but the compute part. Okay. And I think we've come up with some really good examples of where we can spend our compute, though. And one of the big questions is it would be great for the GPU people to find something that's going to sell $100 million, and we're just not there yet. Okay, place of the GPU in tomorrow's computer. So will the GPU continue to be discrete like it is today, where you go buy a board and plug it in? Will it be part of the chipset? Okay, or will it be part of the CPU? And if it's on the CPU, is it going to be part of the CPU die, or is it going to be two dies that are sort of mashed together? Okay? Nobody knows. And the answer is going to depend at least as much on marketing and economics and corporate takeovers as it does on technology. Okay? But that's a big unanswered question, and it's really going to affect the way that GPU computing goes. Design trade-offs and their impact on the programming model. And the really nice way to think about this one is something like SIMD versus MIMD. Okay? Well, you as a programmer would love MIMD. MIMD makes tons of sense. Okay? It's much easier for you as the programmer. You don't have to worry about these branches. They're free. All these threads can go in different directions. That's a design trade-off, though, because if you do something in MIMD, then you're going to pay the price in terms of hardware. Okay? You're not going to have as much data path hardware as you would if it was SIMD. And so what's really the sweet spot there? And so there's a lot of design trade-offs that you do, and they are going to affect the programming model. And this is sort of the place where the hardware and the software intersect. So a place where a lot of research can be done. How does this impact other parallel hardware or software? So one thing I can say about CUDA that's really exciting is now CUDA will compile to multi-core. Okay? You can take a CUDA program, compile it to multi-core, and it's pretty good. That's not the only piece of hardware out there. You would love to have one program that went to multi-core, or GPUs, or the cell processor, or Niagara, or different processors that are out there. How do we build parallel programming models that target many kinds of cores? Okay, that would be pretty cool. Okay, not really done today. That's something actually OpenGL is looking at, though. Sorry, OpenCL, this new language from Apple that a lot of people are working on. They're trying to have more targets than just a single processor, so that's a good thing. Rapid change. So CPUs don't change a lot from generation to generation. And you kind of know where they're going. I mean, we already know what Nehalem's going to look like, right? So what it's Core i7, I think it's called, sort of the next Intel processor. Everybody knows what that processor is going to be. Okay? Nobody knows about what the next GPU is going to be, when it's coming out, what it's going to do. It makes it really hard to plan, right? You write all this code, and then the next year it's obsolete. And that sort of disruption that happens every year or two is good in terms for the vendors because they can make new choices and they aren't held back by the things that came before. But for us as programmers, it's a really hard thing because a lot of our code's obsoleted. So how do we manage this? Okay? What sort of roadmap do we have going forward? What do we know is going to stay good and what's going to change from generation to generation? Okay. How do we measure our performance? And so there's starting to be some good profilers, tuner kinds of things. We'd like to see auto-tuners that will auto-tune code. One of the issues with GPUs a lot, both for graphics and for compute, is this issue of cliffs, where you do this little change and suddenly your performance drops by an order of magnitude. And usually with CPUs, that's sort of a more gentle curve. But with GPUs, a lot of times you do the wrong thing and you pay for it in this enormous way. How do we detect those? How do we build GPU software and hardware systems that are going to make those less cliffy and a little bit more hilly? Faults and lack of precision. So this is an issue of in choosing between accurate and fast, the GPU is traditionally chosen fast. So it's willing to get away with not quite compliant floating point. Okay? It's willing to make, when it does an exponent function, it's going to do, something that's not quite compliant in exchange for making it really fast. That doesn't work if you're trying to do nuclear bomb simulation. Okay? So as it moves toward compute, this idea of having a lack of precision, not having any faults. If you divide by 0 on a GPU, you'll never know. Right? Buyer beware. And so how does that change going forward? More compute and more data structures, more algorithms and data structures. So you guys are going to all do projects. Some of you are going to do GPU computing kind of projects, and you're going to look out and say, what code is out there that I can build from? Where do I get a library that does reductions? I don't want to have to write my own. Well, there isn't a library out there that does reductions. You can sort of rip some code out of the SDK. That's about all you can do. You'd love to have like an STL-like structure that has all these standard algorithms and data structures. Okay? It's just not there yet. And we want more that are easy to plug into. Oh, I just want to get a reduction. This is the way I'll do it. I know it's going to be fast. Okay, and finally, better wedding graphics and GPGPU. I mean, GPGPU people say, well, the best GPU computing application is graphics. Right? It's just an instance of another kind of application. And so sort of the future of where I see the killer app is where you have a graphics pipeline that does some GPU pieces, like say physics or artificial intelligence, where it's part of the pipeline, especially as we design our own pipelines. And so right now it's a little kludgy to take GPU compute results and use them in graphics. It's possible. Just kind of high overhead right now. It's not the easiest thing to use. We'd like to see that get cleaner as things go forward. So these are just big pictures, some of the issues that I see. Those of you looking for projects, these are obviously things that are, these are things we don't have answers for. So projects along these lines are interesting ones. Any questions on these? Okay. Well, we're going to kind of talk about two major things today. One of them is motivating graphics hardware. So why is graphics hardware built the way that it is? Okay. What are sort of the, why do we build it in this task parallel model? And so we're going to go through that again and sort of talk about why, what motivates it? Why did we build it in this way? And then we're going to talk some about technology. And so looking at how things have scaled historically and looking how it's going forward. Because the really important thing, and I hope I'll say this again today, is not so much that technology changes, but that there's lots of things that are changing. Okay? There's number of transistors on a chip. There's speed of transistors. There's the density of transistors. There's power. There's cost of interconnect. All these different things. And it's not so important that they're changing, and they all are. It's how they're changing differently. That this thing is getting much, much better, but this thing's getting worse. And the intersection of two different trends means a lot to us as engineers. That we say, well, looking forward, we can tell that these trends are on this collision course. We really need to build things in a different way. And so we'll sort of talk about that. Okay, so this is sort of a really nice big picture pipeline. I don't think I've showed this particular picture. This is from Pat Hanrahan and Kurt Akeley. I think this is a very interesting, big picture look at the pipeline. And it's sort of expressing it in a stream kind of model. The application is delivering a stream of commands and a stream of primitives of some kind. In this case, we're saying surfaces. So we're sending a bunch of surfaces in. Okay? And that there's all these different steps that we want to do in sort of a generic graphics pipeline. And the way that they've expressed them is kind of interesting, that the gray steps are ones that take a stream of type A and turn it into a stream of type B. Right? So primitive assembly takes a stream of vertices and turns it into a stream of triangles. Rasterization takes a stream of triangles and turns it into a stream of fragments and so on. So that's what the gray steps do. They're sort of streams that convert one thing to another. The green steps are things that convert a stream of type A into a different stream of type A. Right? So operations per fragment take fragments in and fragments out. They're still fragments. They're just fragments, different kinds of fragments. Okay? First, we've taken in all this information per fragment. We're going to put out one color and one depth per fragment. But they're still fragments. So when we start to think about how does the pipeline become programmable, this is only one vision of how we can do it, but it's a very interesting vision about how we can do it. Right now, we have programmable stages at the fragment level and the vertex level, and the new geometry shader we talked a little bit is sort of this primitive level. But we can think of, if we want to do more programmable stages, maybe these are interesting places to put them. And I'd also like to make sure that on all these levels we can talk to global memory if we want to. And historically that hasn't been possible, and that's been more and more possible. So I've been showing this slide for several years, and every year there's a new thing that is implemented. So it's a very nice visionistic kind of slide. Okay, so we implement this in hardware. And we've talked about this slide before, so I'll go over it pretty quickly. We have this big chip, okay, and this is actually a chip of a few years ago. And there's a lot of stuff we can put on the chip. Today we can put 1 billion transistors on a chip. That's pretty exciting. One floating point unit doesn't take up that much room. Okay, that's a double precision floating point unit. Today we can probably fit thousands of them on a chip. So the issues here are compute is cheap. Communication is getting more expensive. Okay, it would be easy to take one clock and send a signal all the way from one side to the other. We didn't have to worry about that. Today we have a clock, and it's going to take multiple cycles to get all the way across the chip. So when I talk about the collision course of technology, this is one of the places where we see this collision. This difference in how computation is changing. Computation is getting really cheap versus communication. And communication isn't changing at all, okay, because the speed of light doesn't change. So these two things are on this collision course, and it really motivates the way we think about technology going forward. We need to build pipelines, build structures such that they take advantage of these trends. One is that we want a trend that exploits ample computation. We're going to have a lot of math to throw at any problem we do. Okay, so we want to build chips, build architectures that have a lot of computation on them. It's cheap. Okay, but we have to do a good job of communicating. The problem is not so much a problem of doing the math. Okay, it's not putting in a bunch of ALUs on this chip. It's a problem of the care and feeding of the ALUs. That's the expensive part. How do you keep them fed with data? That's the hard part. It's pretty easy to put a bunch of FPUs down. Okay, it's hard to have a programming model and hardware that's going to keep them fed with useful data at useful times. Okay, so one of the good things about the GPU has been that it does a very nice job of riding these technology trends. So I made this a few years ago. This is showing, I believe, Pentium 4 numbers in red circles, how fast they're evolving over time. So this is roughly 2000 to 2005, that they're going up 30% a year. Okay, floating point benchmark numbers. But GPUs are doing a better job of exploiting the more computation they have, and it's because they have a more parallel programming model. And so you see both for fill rate, fragments per second, and geometry rate, vertices per second, we see a faster long-term growth. Part of the reason people are excited about GPUs. Hey, can they keep this up? Well, because they're very parallel and they scale well, and they have a programming model that lends themselves well to expanding parallelism, this is a good long-term trend. Okay, and we've seen this at least a couple of times, so I'm not going to go through it again. Let me move a little bit to technology trend here, because this is, I want to spend some time on this. And this is this issue of latency lagging bandwidth. We're going to talk about this in more detail. So the question we have here is, as time goes on, things get better. Okay? Latency gets better, and bandwidth gets better. Okay, and latency, I'm saying, is what's sort of the response time? How long does it take us to do one task? Throughput is sort of how many tasks can we do per second? Okay, so we're not interested in the latency of any individual task. We're really interested in the aggregate, how many things we can do per second. And we've talked before about how CPUs are really latency-oriented kind of processors. We're trying to figure out how to run one thread as fast as we possibly can. What the technology trend is showing here, though, is that when we look at different technologies, and we'll look at these in more detail, we look at memory, we look at disk, network, and microprocessors, and we compare how long it takes to do something versus what's our throughput, we find that throughput is better. Throughput improves more than latency improves. Okay? Latency lags bandwidth. And so this is actually a great paper. I really recommend it. Dave Patterson wrote this. It's in Communications to the ACM. The paper is called Latency Lags Bandwidth. What he says is basically that bandwidth improves as the square of latency. Okay? Bandwidth improves as the square of latency. All right? So this is a good time for me to sort of, I'll go one more slide, and then we'll talk about that in more detail. Okay, so these are some figures that he had in this particular paper. And he wanted to say, okay, how fast are things getting better? Okay, and again, it's not so much the raw number of how much faster they're getting, but it's the differences in how they change. Okay, that compute versus communicate is one of the arguments here. Processor versus memory. Okay, how much faster does this need data versus how fast can this guy supply it? All right, so we have all these different numbers, and he actually did the math. And so this is where I'm going to switch to my other set of slides, and we're going to go through this in more detail. Okay, and I just lost my, we'll see how this goes. Okay, I lost all my speaker notes. That's cool. Okay, so this is the same data that we just saw. Okay, so here's another example of where the collision course between two different trends. Okay, so this has to do with Google's MapReduce. So MapReduce is sort of Google's secret sauce on how they process this enormous amount of data. They're really good at it. And if you take any graduate algorithms class and you're not talking about MapReduce, then you should ask for your money back. So basically, the way they do it is they have this enormous problem to do, and they do a very nice job of splitting it among multiple machines and getting sort of results per machine, and then sort of bringing all those results together. So the map is sort of how you distribute it across multiple machines. The reduce is how you bring all the results together and get a final result. Okay? So they're really good at this. Okay? And what this particular comment said is that MapReduce ended up working and being very successful because it really takes advantage of disk drive throughput as opposed to disk drive latency. There's different ways that we can solve this problem, okay? Maybe my way, okay, maybe the problem I'm looking for is I want all the web pages that have the word Stanley in them. Okay? Well, one way I can do it is build this gigantic database, okay, relational database, the kind we're used to, and go in and search for Stanley in every page, okay, or search for Stanley across all pages. Okay, what these commentators are saying is that the process of going into a database is determined by disk seek time. Okay? Once I say, okay, look for, I say, okay, I need to go get this thing off the disk. Okay? The disk is sort of going around and around and around. There's a head on the disk that moves. And so we have to move the head to the right track, wait for the right data to come underneath and get it. That's called seek time. In general, this is on the order of 10 milliseconds. Okay? It's actually a mechanical process, so it isn't particularly fast. Okay? That's seek time. That's a latency issue. Okay? How long does it take us to go from launching the command to the time we're getting our data back? Okay? So if you're looking for Stanley in a database, then you're going all over the place to get this data. Ding, 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 ding. So basically, your time is going to be dependent on seek time. What Google does, okay, they keep track of their data by always sorting and merging and putting these in particular orders and so on. And so what they do is they stream things through the map process. Okay? So they have all these, they stream it through, and you're just sort of watching this stream go through. And I'm not very good at MapReduce, so don't ask me for specifics, but this is something that takes the streaming part of the disk. Okay? It's not so much based on seek. You're reading this enormous piece of data. And so it's really disk bandwidth, not so much disk latency. And what this commenter is pointing out is that seek time is improving by 5% a year, transfer rate by 20% a year. Latency is getting better by 5% a year. Transfer rate, bandwidth, is getting better at 20% a year. So which curve do you want to be on? Of course you want to be on the bandwidth curve. Okay? Latency lags bandwidth. You want technologies that have to do on the bandwidth curve. I don't know if Google thought about this when they started, but they're certainly on the right curve here. Okay, so Jim Gray is the greatest database guy that ever lived. A couple of years ago, he disappeared on a boat. You probably heard about that. He actually helped us with one of our research projects. Really nice guy. Total tragedy for the community there. But what his point was is that you think of the disk as a sequential device. You think of it like a tape now. Okay? You want to think of it in this bandwidth, the sequential sort of thing. You don't want to think about it as a random access device anymore because you're running the wrong technology curve if you do that. Instead, if you think about it as a giant tape and you read it as a tape and you take advantage of bandwidth, that is better for you. That's the technology curve you want to be on. Okay, so what Dave Patterson did is he sort of went through all these technology performance trends. And he looked at disks and memory and network and processors. And so he sort of went 20 years, okay? Something that maybe none of you ever saw or that maybe your parents had to something that's like today. And sort of to look at bandwidth versus latency for these different pieces of technology. Okay, so if you look at a disk, okay, your first hard disk, how much it had, okay, how fast it was, what the bandwidth was, and what the seek time was is basically what we're looking at. Okay? So we can compare bandwidth here where you got kilobytes a second to what we get now. We're 140 times faster over 20 years. Okay? Seek time, we're only 8 times faster. Okay, so you can plot this over time. And he's got sort of the plot over time, so sort of going 1980 to 2000. Okay? We're definitely on the right side of the technology curve if we're counting on bandwidth. Okay, memory. Okay, asynchronous DRAM that you had in 1980 versus DDR DRAM today. Okay, again, what's the latency? Okay, now we're down to something 4 times as fast. Okay, long latency to okay, and then what's the bandwidth? 120 times. All right. LANs. Okay, doing Ethernet to today. So if you do, I guess this is 10 gigabit Ethernet today versus the standard 10 megabit Ethernet. Okay? So it's 1,000 times more bandwidth today if you buy a 10 gigabit Ethernet, which is kind of expensive, but you can get it. But what's the latency? Okay, it's only 15 times better. Okay? So network here, we can sort of go 10 megabit, 100 megabit, gigabit, 10 gigabit. Okay? Riding the right technology curve there. Okay, CPUs. Okay, so what's the latency of an operation going all the way through the pipeline? Okay, how much better did that get? Well, pipelines get deeper. Okay, it takes a longer time to go through. It takes more pipeline stages, so it gets better, but not that much better. But what's our MIPS? Okay, what's our throughput? Okay, CPUs look great. So CPUs are actually improved more than anything, like in terms of, okay, because that's what we're spending all our money on. So that's really good. Okay, so we talk about the memory wall, sort of the gap between processor and memory. That's what we're looking at here. Memory just isn't getting better as fast as processors are getting better. Okay, so hopefully I've demonstrated to you that latency lags bandwidth. It's a really helpful thing to be able to do. Okay, bandwidth improves as the square of latency. Okay, so then the question is why? Okay, so I got a bunch of slides on why. But why? Why do you think this is the case?
I think one of the reasons why latency is lagging behind is there is always this mechanical interface that happens somewhere along the path. Like if you look at the CPU and the memory, right, the bus interface speed, that kind of has not increased as much as the CPU. Right now you get about, like I think it's 1 gigahertz only now. Few of the chips are coming out of that bus interface speeds. Okay. That's kind of the bottleneck. And right.
I agree with you that those are not going as fast, but if we look at but even if we look at, I mean, like the microprocessor speed up, for instance, that doesn't rely, you know, when we're looking at throughput versus latency, how long it takes us for one instruction versus how many, it's not even counting on the bus there. Okay, the memory speed doesn't matter about the bus. It's just how long does it take us to get from sending an address in to getting data out versus how much data I can do. So I agree with you that there's bottlenecks in there. Okay, but I don't know if that's really getting to the core of the question.
Well, I think bandwidth you can improve with more duplication, and if you have all the space, you can always duplicate, and improve bandwidth. But
okay.
It's kind of a fixed thing. Like you can only get there so fast.
Okay, so this is exactly getting at the heart of the problem. So you can buy more bandwidth. Okay, you want more memory bandwidth. All right, it isn't enough. You pay for twice as many pins. You pay for twice as many banks of DRAM. You've got twice as much bandwidth. If you want twice as much disk bandwidth, buy a second disk. Okay, you can buy more bandwidth, but you can't change the speed of light. Okay, and the speed of light is what's limiting us a lot these days. Right? So when we go into memory, right, you go in, you track around, you have to find the right thing, you have to bring it back. You know, you're limited by the speed of light. So the saying is you can buy more bandwidth, but you can't bribe God. You can't change the speed of light. Okay? So there's some fundamental limitations. You know, money will help you on one, but it's not going to help you on the other. Okay? What are some other thoughts?
I was going to say the same thing.
Say the same thing,
one's
great.
Space limited, while the other one is...
Okay. So expand on that a little. What do you mean by space limited?
Well, if you can manufacture things to be smaller, then you can fit more on a die, and that's the kind of thing that's been happening. They've found ways, you know, to get things smaller, so you can fit more on it.
So how does that help bandwidth?
The closer things are together, the faster it can, you know, travel and communication-wise.
Okay, but shouldn't that help latency too?
It will, but I mean, you can always double it up and double more, so it improves bandwidth more than it improves latency.
Fair enough. Okay, what else?
Doesn't that raise the question of when you reach physical limits of how much you can cram onto a chip? When you reach those physical limits, will not the bandwidth growth taper off?
Well, I mean, that's an interesting question. Okay, what are the physical limits and so on? I think of the graph that I showed, out of those four technologies, there's nothing that's going to stop us in the next 15 or 20 years. I mean, I think people feel that they can continue to improve for quite a while to come. So the question is, I think it would depend on what the physical limit was, whether it would stop latency in its tracks or, you know, if it was, we can't make these chips any bigger, okay, we reach this fundamental limit on size, well, that sort of caps latency because you only have so far to go, okay? But if it's we can't fit any more pins around the outside, well, then that's a different thing. That might cap bandwidth because, well, we can't fit any more pins. We can't send more data off. So, I mean, we'd have to have specific physical limits. The good news is we're not really there. Like, we have more room to run. So I guess we're looking at the point where we haven't hit a physical limit yet. Okay, I'll go through my list because, well, Dave Patterson's list. So this is kind of like Andrew's point. Hey, Moore's law helps bandwidth more than latency. Okay, you get lots of things that get better as Moore's law gets better. You get more transistors and faster transistors. They're both going to help. Bandwidth, but faster transistors versus more transistors. This helps latency, but that doesn't help latency. Okay, having more fins only helps bandwidth, doesn't help latency at all. Okay. Okay. Now, smaller and faster transistors, but as the chips get bigger, okay, the number of transistors you have to run to get from one side to the other, okay, this is sort of our clock cycle kind of thing, where our clock cycle, the distance we can travel in a clock cycle gets smaller. So the latency problem actually gets worse there. So it'll limit our latency as these things change. Okay? Distance limits latency. Okay, so this is where we start to run into physical limits as far as speed of light goes. So, if we look at DRAM, most of our time is spent moving data through the chip. Okay? The electronics are very fast. It's moving data that's really the expensive thing. Okay? Eventually, we're limited, network-wise, speed of light. Okay? Foot a nanosecond. That's as far as we go. Foot a minute would not be so good. Okay. A marketing kind of reason. Okay? We sell throughput. We didn't used to sell throughput. When I was a kid and you bought DRAM at like 80 nanosecond DRAM or 120 nanosecond DRAM. Okay? That isn't the case anymore. Now you buy PC 4400 DRAM. Okay? And they're selling bandwidth. They're not selling latency anymore. Most things sell latency. Right? We don't sell, 1 microsecond Ethernet. We sell 100 megabit. We sell gigabit Ethernet. So because we're concentrating on throughput kind of measurements, that's what people improve because that's what sells. So I thought this was a pretty cool reason. Okay, latency helps bandwidth, but not the other way around. All right, so let's say we can spin our disk faster. Okay, that's going to help latency because well, we can move the head to the right place faster. But it's also going to help bandwidth because if we spin it faster, we can read more data from it. Okay, but not the other way around. Okay, so if we have something more dense, then we can read more data per second. We can get more bandwidth, but that doesn't help the latency at all. Okay, you still have to go all the way around the disk to get, or halfway around the disk to get your thing to the right place. Okay, sometimes bandwidth hurts latency, and so the best example of this is the Department of Motor Vehicles. Many of you have gone to get a driver's license or register a car. How many thought that was a fun experience? Okay, and why is it a bad experience? It's a bad experience because you have to stand in line. Okay, now they're not stupid about this stuff. Your goal in going to the DMV is to minimize latency. You want to be there as little as possible. Their goal in going to the DMV is to maximize throughput. They want to keep their people busy all the time. It doesn't seem that way, but that's what they're really trying to do. And so from their point of view, it's good to have long lines. If you have long lines and you always have people there, then the people at the counter are always busy. Right? Whereas if you went in and half the time there was a line and half the time there wasn't a line, their guys are sitting around twiddling their thumbs all the time. So if there's always a line, they always have something to do. It's because their goal and your goal are entirely different. And if you study queuing theory, you learn about that sort of thing. So bandwidth sometimes hurts latency. These two things are often at odds. And then there's some technical things about operating systems. So in terms of overhead, that now we send things in bigger chunks because that's what gets us more efficiency. And to bundle up these bigger chunks really hurts latency as well. So it's only like a 5-page article. Like the whole first page is like a big picture. There's some nice graphs in there. He'll explain it far better than I did. But it's a really nice thing to keep in mind because all of us will be planning on this throughout our careers. As we design things, we can plan on the fact that bandwidth is going to be advantaged over latency. Okay, let's see. Well, I wanted to go forward. All right, well. Oh, that was the end. Okay, good. That's why I wouldn't go forward. Now I'll be switching back to PowerPoint. Cool. Okay. So now what we're going to do is we're going to look a little bit at characteristics of graphics. So we sort of defined the problem, and we've done this before in class. So we sort of talked about, graphics as an abstract computation kind of thing. What are the things that we think graphics is all about? Okay, so lots of computation. Okay, there's a lot to do. There's more than you can do on a CPU. It's just too much to do. But there's a lot of parallelism. So that makes it tractable. All right, we can build a parallel processor to do all the things that we want. We're able to tolerate a long latency. Okay, and this way we're riding the technology curve in the right way, and that's really important. Okay, but we don't care if the time for one triangle takes 1 microsecond or 5 microseconds. That doesn't care. What we care about is throughput. What this means is we can have very deep pipelines, and graphics pipelines are feed forward. Okay, there isn't these fine-grained loops. Okay, there's not hazards in a graphics pipeline because data only flows one way. Okay, every triangle, every pixel is computed independently. You don't have dependencies between things in the pipeline. Thus, it's feed forward. There aren't hazards. You don't compute something that you need to feed back. Okay, and we deal with some hacks. So we've talked about that a little bit too. So we also talked some about doing time-multiplexed processing. Okay, so this is what we do if we did it on a CPU. So let's say we're going to build a stream processor, and we're going to do it in a time-multiplexed kind of manner. Okay, how do we organize this sort of processor? Okay, well, what we need to build is a set of kernel processors here that are going to be able to handle all the math we'd like to do. There's probably some parallelism in there. And keep in mind when we build a stream processor, we don't build, we have different kind of locality than we would necessarily get if we just had a general purpose processor. We talked about this. You don't get a lot of reuse out of a stream processing system. In general, you read something once, and then you write something once, and then you go on to the next thing. So every item is written once when it's produced, read when it's consumed. Okay, there's not any reuse. You're not going to read something multiple times. So what we don't want so much is a cache. Instead, we're going to create some sort of structure that's going to capture producer-consumer locality. Okay? And that's what we, let's see, stream register file, something to store temporary streams. That's what makes some sense there. So if you're going to build a processor that's sort of optimized for throughput, but you're going to do it in a time-multiplexed manner, this is kind of what it's going to look like. Okay? This, something pretty parallel, hopefully. Okay? Maybe you'll have a small control unit that does a bunch of parallel things. This is something that's organized differently from a cache. Okay? You want to think about this keeping track of producer-consumer locality best you can, rather than something automatically managed as a cache. So just keep that in mind. Now, you can probably use a cache to do this, and that's why people are interested in doing more manual memory management. So you have instructions in your instruction set that are going to allow you to control the cache in non-automatic ways. You're going to be able to say, oh, I want to make sure I cache this, or this is something that's going to be uncached. And if you look at something like the cell processor, you have complete user control over their stream storage. Every one of their kernel processors, their SPUs, has its own bundle of stream storage that you get to use however you want. Okay? You're responsible for managing your own memory.
Since you're only handling like one unit at a time, do you want really, really high bandwidth between the stream storage and kernel processor, I would guess, right?
Well, you hope so.
If not, it's a lot of memory, like waiting for things to load. So
the nice part is that the bandwidth you can get on chip is generally very high. So roughly, if we say the bandwidth from here to here is X, okay? So off-chip bandwidth is X. Then global on-chip bandwidth is generally on the order of 10 times X. And local on-chip bandwidth, like where you're just communicating with your neighbor over like all the kernel processors where you presumably do work, that's like 100 times X. Okay? So the nice part is if you manage it nicely, you can get 10 times the bandwidth you'd get if you had to go off chip for it. Okay? So this is part of the care and feeding thing. You want to make sure that this is able to keep this guy fed. And you want to make this big enough and wide enough to be able to do that. Okay. So why don't we use microprocessors for this? Well, hopefully that's something that we've talked about a little bit. They're really doing something different. Okay? They're really interested in latency-oriented processing. And so they have very complicated control, not so much data path, optimized for latency, not bandwidth. And so when we look at sort of the die area that's actually devoted to doing compute, it's pretty small. And I'll show that even more in another picture. So this is an old picture, right? Pentium 3 is pretty old at this point. But this is the whole chip. This is the part of the chip that actually does compute, right? It gets even smaller as we move forward because of these very complicated caching and big control structures. Okay? This isn't designed to do lots of computation. This is designed to do one thread really fast. Okay, so if we go forward here and we look at the Deerhound die, we looked at this in the first class, right? Okay, so what I've shown in red here is the parts that do compute. So it's even a smaller fraction of doing compute than we saw before. So last time I showed this slide in a public talk, they said it looked like a carpet, like a big rug. Anyway, so this is all the places we do compute on this. Everything else is control and storage. So this is the entire integer pipeline, that little box right there. Okay, that's not very much. This is 3D Now, which is AMD specific, some graphics extensions. So that lets you do graphics on the CPU. This is all the floating point stuff, and most of that is SSE. So we start to have parallel graphics, 4 things at once. That's where most of your area is going. So there's more data path because they're able to do 4 things at once. But if we look at a GPU, and I wish they'd give us the die, this is something that would hopefully, and I would expect, would have a lot more data path on it than what we see here. Okay, so if we look at the task parallel sort of model, we can talk about why graphics hardware is fast. So these are the things that we'd like to be able to do with graphics, right? We said our characteristics of graphics. How does a task parallel model help us take advantage of that? Well, lots of computational requirements, but we have lots of different functional units on the chip. There's parallelism within each one of those. Hopefully, we can put a lot of different processors on this chip, all of whom are working at the same time. Okay? So lots of units, and each one of these is very wide. Okay, so that's a plus. Long latency is tolerable. And that's part of the reason we can have this long feed-forward kind of pipeline here, right? This is a really deep pipeline. Each one of these is individually pipelined. Any piece of data has to start here and run through all this stuff before it finally gets to the end. Okay? But we can tolerate that sort of latency. If we have those really deep pipelines, hopefully that's something that's going to let us keep lots of different units busy. All these guys can be running simultaneously on different data and have parallelism within here. So this is why people have historically built graphics processors in this way. Okay? All this stuff, plus the fact that you can customize this to do its particular task. This is the way they felt they could throw the most computation on the chip and keep it busy. It's not just having a lot of computation, it's being able to keep it fed. And this is a structure with very simple control structures and these deep pipelines with lots of latency tolerance that's well suited for keeping it fed. So if we actually look at a chip, and again, I wish I had a better GPU to show you here. Okay, this is the ATI Flipper. So this is the core of the Nintendo 64. All right, so some of you have seen this before, maybe. This is a little bit different than most GPUs because it actually has the frame buffer on chip to save money. All right, so they didn't want to have to do like a chip, a processor, and then have to buy DRAM for it. They wanted it cheaper. So they actually had a fairly expensive process to do this, but they were able to have an embedded frame buffer here, so DRAM here. Now, one of the reasons they could get away with this is the Nintendo 64 basically spat out to a TV set, right? You didn't have HD capability on a Nintendo 64. And so a TV set really doesn't have a lot of resolution. You can have a pretty small frame buffer. It's like 500 by 300 or so, right? So it's pretty small. And you can probably fit it all on chip if you want to. Can't really do HD that way. You know, it's hard to do 2000 by 1500 or roughly whatever HD is. But they spent the extra money to be able to do this so that it would end up reducing overall system cost. So this is task parallel. So the reason I have this picture is that each one of these units is very clearly a different unit in the graphics pipeline. XF is triangle transform, for instance. Okay, SU is triangle setup. These are 2 rasterizers here. This calculates color in Z. These are the texture units. That does texture fetch, texture color, texture environment kinds of things.
I was just curious, why is it so hard to add? It seems like if you had a frame buffer designed for a separate chip, you could just pick that circuit design and plop it down in that corner. I guess I'm just trying to figure out what makes it so hard to add something like that.
Okay, so a big part of the issue is that you have one flow, design flow, one set of technology flow that does CMOS, and a totally different technology flow that does DRAM. So DRAM transistors today are tunneling, and they're sort of turned vertically. It's a trench transistor. So if you look at CMOS kind of stuff, it's basically all on the surface. Okay? To make DRAM really dense, they take the surface things and they basically dig holes in it. I'm not an expert at this in any way, but it's basically a vertical structure that goes down into the chip. So pretty much most structures either do one or the other. Okay? So if you want a hybrid process that does both, that costs more money. So part of it is expense. I don't have this great, so even if you're willing to spend that money, the question is, why don't you do that? Why doesn't it make sense to be able to do that? Think of how fast it would be. Think of the great bandwidth you would have. Think of the latency you would save. And I guess the only answer I can say is, you got to figure the guys at these companies are not stupid. And you got to figure that they looked and said, is it more profitable for us in terms of design to use these transistors to put some DRAM on the chip? Or is it more profitable for us to put it off the chip, spend a little bit more money, and use those transistors to get better graphics? And I guess we can see from history that the answer has been better graphics. Okay? It's been more worth it for them to use those transistors for something else. So I haven't really seen a lot of embedded DRAM processes recently, so I guess nobody's really putting these together anymore, or nobody's found a way to make it economically worthwhile. It's a really good question. This is a really good thing for you to ask some of our visitors that are coming. Hey, why aren't you guys doing this? That being said, there's a lot of storage on the chip. So I know there's 6 megabytes of registers alone on the NVIDIA compute units. 6 megabytes. That's a lot for registers, right? So they're just using it a different way, and they don't keep the whole frame buffer. Because I guess part of the problem is you say, oh, frame buffer, it's just a TV screen. But frame buffers are deep. They have lots of information associated with them. Their use is growing just like the rest of the graphics pipeline. It's not like they're just storing one color and one depth. They're storing lots of things per pixel often. Good question. I hope you ask the people that come to visit. Okay. So I like the picture because it's got, it shows the task parallel view of how these things are built. So each one of these guys is hardwired to its particular task. Lots of computation, because every one of these guys has its own computation. Producer, consumer, locality, right? You want to produce something and immediately consume it, and you want that to be efficient. And when you put two things next to each other, it's going to be really efficient. He produces it, just feeds it to the next guy. It works very nicely in a pipeline kind of structure. So that's kind of cool. The communication patterns are very efficient. Okay, so if we sort of contrast these two, task parallel, time multiplexed, something to keep in mind because different technology constraints might make you think about one or the other. And the move with graphics hardware today is to move from a task parallel approach to a time multiplexed approach. And there's really a couple reasons. One is flexibility. Okay? We want things to be more programmable. In general, the time multiplex approach kind of has to be programmable at its core because your set of functional units has to be able to do the whole pipeline. So it pretty much has to be very flexible and very programmable. Whereas in the task parallel world, each part does its own little task, and so you can probably hardwire that. So it's desirable to have more programmability. We might want to move this way. The other thing that really became an issue is this issue of load balance. Okay? When you have a task parallel approach, you're going to be limited in performance by the slowest one of your stages. And that load balance has been an increasing problem as stages became wildly different because of programmability. And so the move has been more in this direction. So my dissertation work was showing that this was a good idea. Right? That was sort of the biggest picture of the things that I did for my dissertation. So it's kind of nice that it's moving in this direction, but I didn't really expect it was going to happen quite in this way. Because this specialization has been an enormous win. Okay? But what we're going to see from the guys who come to visit from Intel, they're going to say, we think even the things that you specialize on are things that we can build very efficiently in software. So for me, the last thing that you really wanted to do in programmable logic is a rasterizer. Okay? Rasterization turns out there's really nice hardware algorithms to be able to do it. You're going to spend just tons of effort in being able to do it in software. Okay? But they have said, we think we can do it in software. And part of the reason they said they could do it in software is that they got to design their own instruction set. And so they picked instructions that were very well suited for rasterization. And that sort of reduced the penalty of not having specialization, and they think they can do it in software. They think they can rasterize things in very few instructions. So it's, they haven't released details of this yet. I really encourage you to ask Matt when he comes to talk about it. I'm very interested to hear more about this because I know rasterization is a hard problem. Okay, any questions here?
But if you design special instructions for, like, you know, like what you said, the rasterization instruction, you're only going to use it during that stage. So why even bother having that instruction?
Because it really helps in that stage. I mean, their job is, so, okay, they have a few jobs. One job is to say, what do we need to do so that rasterization is not a limit? What is the cheapest way to do that? Okay? Our whole goal is to make sure that rasterization is not going to be a bottleneck. All right? Is it cheaper for us to build our standalone rasterizer? Okay, in which case you only use it for rasterization. Or is it cheaper for us to put a few more instructions in the instruction set? Intel's answer is, we're going to put some more in the instruction set. Okay? I could make an argument either way why they're better. NVIDIA obviously makes a different decision. NVIDIA says, well, we could take our compute units and make them better able to do rasterization and put in some instructions, or we could do it as a rasterizer. Okay? NVIDIA chose rasterizer. Intel chose software. Okay? So presumably they're not too far apart in terms of, well, I don't know. I mean, it's a great question to ask our guests when they come also. Okay? They both had the same data, and they analyzed it differently and came up with a different answer. Question?
Yeah, I mean, what special, is there any special neat tricks that you could use with a programmable rasterizer that you know of off the top of your head that would be, you know, game-changing?
Well, I mean, one good thing about specialization is you build it to do its one task. Okay? The bad thing about specialization is that it only does that one task. So you want to do a different rasterization algorithm, or you decide you don't want to do it perspective correct, but you want to put in these other tweaks into it to make it do something else. Well, it's pretty much impossible when you do it in a specialized hardwired rasterizer. The question is, how will they use it? How will they use those? Do they have okay, so here's a good example. One thing we're going to learn, or hopefully you're going to see in your project, is that if we look at triangle size, okay, how much work does it take to rasterize a triangle? Well, if you say that there is a certain amount of work that's fixed, every triangle has to do a fixed amount of work, and we'll learn about this when we do rasterization part. Okay, every part has a fixed amount of work. Every triangle has a fixed amount of work, and then you do a certain amount of work per fragment you generate. Okay, so big triangles are going to take longer than small triangles because there's more fragments to generate. Okay, what does this say as far as the cost? Okay, so size versus cost. Okay, this graph makes sense, right? This is kind of how we'd think of how expensive it would be to rasterize a triangle. Okay, well, when you're NVIDIA and you build a hardware rasterizer, you have to pick one particular place on this curve and say, we're going to build the rasterizer for that. Okay, and we know that that point right now is about 8 pixels per triangle. Okay, that might be the crossover point you find, for instance, right? They designed for that point. Okay, now if you're Intel, then you say, and so NVIDIA builds it here. So what can you do with a software rasterizer? Well, you might build a rasterizer here. Okay, and say, if a bunch of little tiny triangles come through the pipeline, then we're going to run this rasterizer. If that's followed by a bunch of other triangles that come through and they're gigantic, we're going to switch rasterizers to something else. Okay? You might be able to come up with different rasterization algorithms that work in different ways. And in that way, you're really taking advantage of your software. And you can target it to different points on this curve. Okay? That would be pretty cool. I don't know how they're doing on that. But I would imagine they're going to look at that sort of thing. Okay. So we're going to do a little bit of looking at technology scaling here. Okay? These are also graphs we're going to look at, but we're going to look at them a little bit in terms of this. So how do things get better? Okay, so SGI pretty much came out with a new flagship product every 4 years. Okay? So what got better here? Okay, well, everything got better. Okay? I'm trying to think of the exact point I want to make here. Okay. One of the big points is this growth curve here. Okay? Things are getting 120% better every year when you look at Z-buffered triangles and fill rate and triangle rate. okay, which is really pretty remarkable. So they're getting more than twice as good every year. Okay? If you measure it just regular triangles and regular fill without a Z-buffer, well, it's a different sort of numbers. But kind of, I mean, everybody uses Z-buffered triangles and Z-buffered hill. There's not really a perfect way to measure this, but this is one good way to measure this. Okay? So, getting much, much better every year. Okay? NVIDIA also claimed a similar growth rate here. I find this is one of their worst marketing slides ever. This whole Moore's Law cube thing seemed like a big crock to me. But to look at how much faster things are getting there. When you look at millions of polygons you can draw per second and fill. Okay? These ended up being similar performance sort of curves that were happening here. Okay? And then eventually we get up to their historicals here, and I sort of, this is my set of numbers that I've been compiling. I don't think I've showed these before, but just to show how much faster things are getting every year. Okay? So if we look at millions of transistors, okay, 65% more transistors every year, okay, 62% more fill every year, and pretty much doubling the vertex rate every year. So it isn't quite as fast as NVIDIA's historicals, but it's still a really good growth curve, and it's certainly above what you get out of spec when you're looking at CPU kind of performance. So they are able to take these numbers and more resources every year and be able to get more and more performance out of it, which is really a good thing. Okay, so I want to talk a little bit about this international technology roadmap that's going on. So these are old slides. They release this roadmap every few years. It doesn't change an enormous amount, but basically the international technology roadmap is this giant collective hallucination on the part of the semiconductor industry. There's all these pieces of the semiconductor industry. There's the guys that build chips. There's the guys that design chips. They're the guys that build the wafers that the chips go on. They're the guys that build the devices that handle the wafers that the chips go on. They're the guys that design all the chemical baths that the devices go on, and the cutting units and the testing units and so on. All these different pieces of the chip industry. And so the problem is you say, okay, well, I'm going to build this awesome machine that handles bigger wafers than we had before. Okay? I'm going to build a machine that handles wafers that are as big as a pizza. Okay, well, who's going to use those wafers? And who's going to build those wafers? Well, you're not really sure. Okay, so you're not going to build your machine because nobody else is really committed to either giving you the wafers or giving you the or using them when you're done. So then you don't get any progress. Nobody's willing to sort of be the first guy to step up and say, all right, I'm going to build the new technology here, and hopefully all you guys are going to come along after me. So what this international technology roadmap does is you get all these suppliers and you lock them in a room together and you say, all you guys are going to agree to go forward. Okay, you're all going to go forward together. And what's going to happen in the next generation? So then they get together and say, well, we'd really like to have chips the size or wafers the size of a pizza. So, okay, you're going to have to design these wafers, and you can plan on them being the size of a pizza because that guy's going to build the equipment that handles them, and this guy's going to build the conveyor belt that moves it along. And so everybody sort of agrees, okay, if I do my little part and everybody else does their part, then we're cool. Okay? Then we sort of move forward in technology altogether. What happened before they had this is sort of the first person to develop the new technology spent all this money to prove the technology was possible, and they built something and then they just get absolutely crushed because they spent all this development effort. Then the guys that came after them said, oh, now it's possible and this is how you do it, and they'd build it much cheaper and they'd make millions of dollars. Okay? That didn't help things move along very fast because nobody wanted to be the first guy. Here, everybody's the first guy together. So, what they publish is a set of projections, how things are going to go. Okay? So this is starting in 2001. So this one up here is the pitch of basically how far it is between transistors. Essentially, this corresponds to channel length in a transistor. So when you talk about a process being like 0.45 nanometers, this is what you're talking about. So at the very beginning, the pitch for DRAM and microprocessors was different, but pretty much they've converged. The semiconductor industry has stayed spot on target here. Okay? Basically, it's every year it goes down. It goes to 70% of its previous value. That's exactly the curve you're looking at. They are spot on. This curve is clock speed. Okay, so what they said is in 2000, we're going to be running at 2 gigahertz. In 2009, we're going to be at 10 gigahertz. Okay? So they weren't quite right here. Okay? But it's important to point out that if they wanted to build a 10 gigahertz processor today, they could. Okay? It is technically possible to build a 10 gigahertz processor today. It is not possible to keep that processor cool. Okay? So it's going to melt. But you could build it. Okay? So we've changed the way things go. This is how many transistors you put on a chip. Okay? So what we're saying is roughly by 2007 or so, you can put 1 billion transistors on a chip. And roughly that's right. There may be a little bit off, but if you go by the latest NVIDIA GPU today, that is a 1 billion transistor chip. So this one, they've been pretty much right on. That one over there is the number of basically pins you have. Okay? Notice it's not growing quite as fast as some of these other ones. And so it's important that you understand what the differences are between these. Okay? This is a bandwidth limitation, right? You're not going to have too many more pins. It doesn't grow particularly fast. If you're going to improve your bandwidth, you're going to need to run the pins much, much faster. Okay, so this is the one that they were really, they were correct on, but they didn't realize it was going to be such a hit. This is power. This is max power per chip. Okay? What they basically said is 2000, 2006, we can get up to about 200 watts. We can't keep anything cool anymore. Okay? We can't have any chips that go more than 200 watts. And the problem is that these two things don't really work out together. And what they found is that the power cost of their chip went up faster than they expected them to. Okay? They expected they would run cooler than they did. They found out they had a lot more leakage. They found out they didn't scale as nicely as they could. They stopped being able to scale voltage. And so as this went up, the power went up more quickly than they expected, and they ran into this wall. Okay? So this is what's really motivating parallelism. And I have a bunch of slides I'm not really going to get to where I talk about sort of what the real technical meat is behind why parallelism is a good idea, okay, based on these technology trends. But this is really this is the power wall that we're running into. Okay? We can't keep things cool. Okay, so I did a projection a few years ago, and this is just sort of using semiconductor and historical kind of data. How much do things go forward? Okay, so this was done in 2004. And so what we're looking at is the baseline here was the NV40. I think that was GeForce like 7800 or so. Okay, so I looked at how many transistors does this guy have, and what are we going to see in 10 years? So basically, we're at the halfway point right now. So basically, we're going to have 10 times as many transistors. In 10 years, you're going to have a 2 billion transistor chip. And that seems like it's probably going to happen. Okay? Clock speed. All right? So that chip ran at 475 megahertz. Today we're up to, I believe we run at 1.35 gigahertz on the latest NVIDIA chips. That's how fast their compute units run. Okay? So this seems like it was a pretty good prediction. So if you multiply transistors by clock speed, you have what we call capability. Okay? Right? You have more transistors and you run them faster. Okay? So basically, how many times can you switch a transistor per second, or how many transistors can you switch per second? Okay? So that's going up a lot. Okay? In 10 years, we should have 40 times as much capability. Okay? That's probably going to happen. How much memory bandwidth? Okay? Well, if you buy the top end, I think the ATI chips have the high, no, NVIDIA has the highest bandwidth now. That's a chip that's getting roughly, what are we up to? It's like 130 gigabytes per second. Okay, so we got a little ways to go there. We'll see if we make that. Okay, memory latency. Okay, remember the latency doesn't get better very fast. It goes from 40 nanosecond to 23 nanoseconds. So we'll not even get 2 times as good. Okay, and then power. Okay, the International Technology Roadmap basically said we make it up to 198 watts and it's flat. So what the important point is for you is to see that historically, and what we envision in the future, the capability gets better faster than the bandwidth, gets better faster than the latency. Okay, that's really the take-home point here. Okay, and that's something we can continue to count on as we build new graphics architectures. So if you look at the difference of these two things, okay, the memory bandwidth and the memory latency, and we talked about bandwidth and latency earlier, generally we call this the memory wall. Okay, and this has been this ongoing problem since pretty much early 1990s. They said, boy, this is really coming at us fast, right? Microprocessors are improving faster than our memory is improving. The response to this that made us continue to be able to get better and better performance year after year is cache memory. Okay? Early computers, there wasn't any cache memory. Cache memory is the only thing that's helping us fill this gap. And it's why we moved from 1 level of cache to 2 levels of cache to 3 levels of cache and so on. It's the only thing that's making this tolerable. Otherwise, we'd be completely limited by the fact that the latency here only gets better 7% a year. Okay? So our two sort of big walls we face are the memory wall and more recently the power wall. Okay? That's maybe a harder one to get past. But this is an example of a divergence of technology that you need to understand and say, this is really going to motivate things going forward. We do need caches. We do need to close this gap best we can. Okay. So kind of for the rest of this class, whenever I'm speaking, these are going to be things I'm going to point out. All right, so we can look at technology, and we're going to say, what does technology give us? What are we going to do going forward? Okay? We know that we're going to have more transistors and higher clock speeds. We know that we're going to have a lot more capability. The question is, what are we going to do with it? Okay? We know that the ratio between off-chip bandwidth and computation are changing, okay, in favor of computation. Computation is getting cheaper. We're going to want to change graphics architecture in response to that trend. And we don't get to have on-chip communication speeding up very much, because chips are getting bigger and it's taking a longer amount of clocks to get from one side to the other. We don't want to do global communication on chip. All right? So if we have more transistors and higher clock speeds, what do? Okay? Faster processing. Right? We can run more stuff, we can run it faster and so on. We're all familiar with this. Okay? And put on more features. And we have lots of opportunities here. We can do new graphics things you couldn't do before. We can do programmability. Right? We can start putting things on the chip that let us optimize communication. Okay, that would be pretty cool. We do a lot of compiler work right now. Do lots of things in the driver. So let's instead put some of those features in the hardware. We have more transistors to play with. We're willing to pay that. Okay, how do we make it easier on the programmer? Okay, we'll put more performance monitors on the chip so that we can do better profiling kinds of stuff. Okay, that's worth our transistors. Better quality. Okay, we're not going to do things in integer anymore. We're going to do floating point. We're going to do more precision. We're going to have double precision floating point. Okay, so this is how we can use more transistors. Okay, and we'll be pointing these out as we look at specific stages of the pipeline. Okay, the issue of our memory wall. Okay, our real goal here is to reduce bandwidth from off-chip because bandwidth is getting more expensive. How do we do that? Well, we need to reduce vertex bandwidth. Okay, how do we do that? Can we do, there's different techniques there. We want to reduce texture bandwidth, and we'll talk about that a lot. Okay, different ways to do this. Bandwidth of the frame buffer, how do we do this? And so a lot of what we'll talk about is ways to eliminate these bottlenecks. In general, we would prefer to compute rather than communicate. Okay, we might have the choice to go out and get an item from a texture or to compute the texture locally. More and more, it's going to be cheaper to compute the texture locally so that we don't have to communicate. And what David Patterson says in terms of this basically bandwidth versus compute kind of argument is there's three things we want to be able to do. We want to cache, we want to replicate when we need to so we don't have to communicate, and we want to predict. Okay? So we'll talk mostly about this because this is how mostly people have done it, but these are other ways that we can address this sort of problem to eliminate this bandwidth bottleneck. Okay. And the final thing is how do we reduce on-chip communication? Okay, well, we need to reduce on-chip communication. We do that by replicating, by compute rather than communicate. And it's very important also in on-chip communication that we reduce power. Okay, because that's important. And so it's important that we don't communicate both because it's slow and because it costs a lot of power. Okay, this seemed like a good summary. Anybody have any questions about this? Okay, so this is the most VLSI hardware-y kind of thing that we're going to talk about this quarter. What we're going to be doing for the next few is we're going to go through pieces of the graphics pipeline. Okay, we're going to look at the geometry stage, and we're going to look at what happens in the geometry stage, and what are the computations that we need to do. So we'll look at, okay, how is lighting actually computed? What do we do? We're going to look at like clipping and culling. How do they actually work? We're going to look at the transformations that we need to do. How do they work? So what are the different pieces in there so that we understand what the algorithms are and why they work? So basically there's four big things that we're going to talk about. One is the geometry part of the pipeline. One is rasterization. Okay, how do we take triangles and turn them into fragments? Okay, one is texturing. How does this texture pipeline work? Lots of cool techniques in there. And the last one is composition. How do you put things together when we're all done and as it moves out to displays? Okay, so that's going to basically take 5 lectures to go through those 4 pieces of the pipeline. There's some more lectures after that, but that's at least the direction that we're going. Week from Thursday, we're also going to have our first guest speaker. So basically 5 Thursdays in a row, we're going to have guest speakers. I particularly want you to come here and be attentive on those days. Good day to drink your coffee. Make sure you're ready to go. I'll be inviting, grad students to the graphics lab and so on. So I hope we're going to have full seats here. But I want you to really look at this as a learning experience. These are really the top people in the field. They're going to have lots of great things to say. I'm very excited about having them out here, and make sure you take advantage of that. Okay, I'm done for today. I'll see you guys on Thursday.